Thanks again, everyone, for coming out here. So I'll be focusing on the climate science part of these lectures. I'll be doing a talk today and another talk tomorrow. The one tomorrow will build on what we're going to learn today. And to introduce myself, I'm Justin Bandoro. I'm a PhD student in the program in Atmospheres, Oceans, and Climate. So that's course 12 here at MIT. And my area of focus is on atmospheric science and has to do with the layer of the atmosphere called the stratosphere, which we'll learn more about today. So, so the purpose of these lectures is to develop a broad understanding of the Earth climate system. So referring to what Christoph was showing with his whole model, we're going to be learning about the science for the Earth system part of that, so the Earth system, so focusing on that. And so today we're going to focus on the first bullet point, which is to develop a broad understanding of it. And then tomorrow we'll look at how the climate system can respond to different natural and human-caused changes. And like he said, I'm not focusing on the policy, economics, or governance. These lectures are the science. And today's topics we're going to touch on the history of climate science, and then go into the structure and composition of Earth's atmosphere, and then look at Earth's energy budget and how greenhouse gases can affect Earth's energy budget and warm the surface, and then look at different lengths of variability in the climate system that range from anywhere from a year to hundreds of thousands of years. And then the last topic will be on the emissions of greenhouse gases and their long-lived persistence in the atmosphere. Great. So this is a cool animation developed by scientists at NASA. So this is going back to 1850 and looking at the temperature change since 1850. And as it goes around in this circle, it'll repeat. It's showing the months around the circle, and then showing the temperature change since 1850. And yeah, so you can see it's going out, and the color code is purple is relatively colder and yellow is warmer. So you can see as it progresses, there's two important things to note. The first is that some years you can see it contracts inwards and then comes back outwards, which shows the variability in the system. So that so it's not saying that every year is getting warmer and warmer. Of course, other years where it spreads out and goes inwards, but you can see the overall trend where the Earth has warmed globally. So yes, so this is a global average. It is globally around 0.8 degrees Celsius. So today we're going to try to understand what can be causing this. So to start off with the definitions of climate, the popular definitions could be it's the average of weather. The other one is it's what you expect, and weather is what you get. But here we're going to be, the climate is the statistics of weather. So it's over time you accumulate more and more information. You can get the mean of the weather, but also the variability. So it's aggregations over time scales of more than 1 year, and so that the seasonal cycle is not considered. And examples of climate variability are what most of you have probably heard of is El Nino, La Nina. So I'll talk more about this later, and that just has to do with the warming or cooling over the Eastern Pacific equatorial ocean, and that affects weather all across the globe. And then another length scale is the Little Ice Age. So that was around in the 1600s, where the Dutch were skating on canals to work, and this is just an example of where there could be periods that are colder or warmer than others. And then on the longer time scale, you can have these glacial cycles, which are anywhere from 20 to 100,000 years. And for example of this is where glaciers covered most of a large part of the North America, and reached all the way down here to Boston. Right. So to start off with, we'll just delve into the history of climate science and the greenhouse effect. So this is we'll get into the science more behind it. So it's just that some gases in the atmosphere absorb infrared radiation, and they re-emit it back down to the surface, which causes a warming effect. But this was actually first known in the late 1700s by John Fourier, and he first understood what was going on, that some of these gases would absorb it and re-emit it, so they'd get warmer. But it wasn't first quantified until John Tyndall in the mid-1800s, where he built an apparatus. He built an apparatus that could actually quantitatively measure how much absorption there is from certain greenhouse gases. And then continuing on, this was Svante Arrhenius in the late 1800s and early 1900s. He actually was able to, without any of the global climate models we have these days, he was able to figure out that, or estimate that any doubling of the percentage of carbon dioxide in the air would raise the temperature of the Earth by 4 degrees. So he knew this, or he was able to estimate this in the late 1800s, and surprisingly, this number here, which we'll learn about in tomorrow's lecture, which is the climate sensitivity, is pretty in the middle of what estimates we have today. And lastly, this man, Milutin Milankovitch, in the early 1900s, he solved the mystery of the ice ages. So the ice ages occur because in the northern hemisphere, it receives a little more or less solar insolation during the summer season, and the reasons for this have to do with Earth's eccentricity. So this is, if you think about how circular Earth's orbit is, because it's not a perfect circle, but how circular it is, or the eccentricity, changes with a period of 100,000 years. And there's also the obliquity. So because we have seasons, Earth's axis isn't exactly perpendicular to its orbit, so it's tilted. And this tilt varies around 2.5 degrees. It's at 23 degrees, but it can vary up to 2 degrees. And that has a period of around 41,000 years. And lastly, you can think there's also precession, so that's how much it wobbles around its axis. So you can think of it as like spinning a top. When the top's about to die, you notice it starts wobbling around. That's what's called precession. So all of these together, the combination of all these 41,000, the 20,000, the 100,000 year cycles together, that can explain the ice ages, because it has differences in how much solar insolation the Earth is receiving in the summer season in the northern hemisphere.
Obliquity again?
Sorry? Sorry. So obliquity, you can think of it as like, so Earth's axis isn't perpendicular, so it's actually tilted.
Yeah.
So when it's going around the sun, it's actually tilted.
Well, it's staying that constant tilt.
Yeah, so it stays at that tilt, but then the amount of that tilt varies.
It varies.
Yeah,
so
so
that's the
it doesn't.
factor.
Yeah, so it varies by around 2.5 degrees, like that way. And that will, if you think about it, depending on which season you're in, you'll receive more sunlight than depending on if it was tilted in the other direction. Right. So we'll start with the structure of the atmosphere. So the atmosphere is divided commonly into 4 different layers. And so the troposphere, which is also called the weather layer, that goes from the Earth's surface to about 10 kilometers. And this is so I said where all the weather happens, it's the cloud tops. They only get up to 10 kilometers here. And this is usually, right under here is usually the level that planes fly at. And you can see so this is showing temperature with respect to height. Kilometers on the left, miles on the right-hand side. And you can see temperature decreases with height in the troposphere. And then the second layer, which contains both the stratosphere and the mesosphere, is the middle atmosphere. In the stratosphere, what's interesting to note is that the temperature turns around and starts increasing back with height. And this has to do with the ozone layer that you've all probably heard of, which is it peaks around 30 kilometers in the stratosphere, and ozone absorbs solar UV radiation, and that's what causes this layer to warm up. And then you can notice these things called the tropopause, stratopause, and mesopause. these are just points where the gradient, or not the gradient, the temperature turns around. So it turns from cooling with height to or warming with height, and then in the mesosphere it decreases back again. And finally, way up over 90 kilometers, you have the thermosphere where temperature turns back around and increases with height, and this has to do with interaction with charged particles from the sun that heat up this area. But for these lectures, we don't really have to consider the mesosphere and the thermosphere, and we'll be focusing on the troposphere and the stratosphere, because that's what's important for climate. And another thing to note is the atmosphere is very thin compared to the radius of the Earth. So if you look up here, going from 0 to 130 kilometers, well, the radius of the Earth is around 6,000 kilometers. So it's very small compared to the radius of the Earth.
Sorry,
Yes.
which region are the satellites?
Oh, right. So the satellites, well, depending on which orbit they're in, some of them are right at the low end of right above the mesopods, and some of them can be way up higher. Okay. Right. So this is showing Earth's or the temperature climatology of the Earth. So it's showing the average temperature for a given month. So this is going through from January to December. So this is averaged over 40 years. And the color bar, this is well below freezing. And then hot, and then red is maybe around 20 to 30 degrees Celsius. So it's showing how much just the average temperatures over the globe. And what you can notice is that this belt of warm temperatures around the tropics, it shifts northward or southward depending on the season. And then in certain areas, like given in Siberia, you can see changes of around 50 degrees Celsius from summer to winter, while in the tropics, some of these regions only have a change of around 3 degrees Celsius. So you get more extreme variations in the high latitudes in the northern hemisphere. And the other thing you might notice is that in the southern hemisphere, the changes aren't as drastic. You can see over here, they're very drastic. It's not as drastic over the southern hemisphere, and that's because a large portion there is ocean, and in the northern hemisphere is where we have more of the land. So the ocean allows it, damps out the seasonal variability in the southern hemisphere. And this is showing the same thing, but for sea surface temperatures. And you'll notice again, you have the warm belt over the tropics, but it's not zonally symmetric. So what that means is there's regions where the ocean is much warmer than others. And other features to note are, you can see the Gulf Stream coming up here for North America that brings warmer water up our east coast and over to Europe, and the Kuroshio Current in Japan. So this is just to show broad view of the average, what we can think of the average temperatures on land and also the ocean. So next part we're going to look at is atmospheric composition. So this is a pie chart, and blue is nitrogen, so N2, and red is oxygen, O2. And the first thing that stands out to you is that most of the atmosphere is nitrogen and oxygen. So 78% nitrogen, 20% oxygen, and you only have this tiny sliver here, 1% is argon, and you have this tiny slivers here with water vapor, which is 0.4%, and these trace gases, which include carbon dioxide, methane, and other inert gases, and also ozone and nitrous oxide.
Sorry,
Yes.
this is everything below stratosphere?
Yes. Yeah. Well, there's not much above the stratosphere. 80% of the mass is in the troposphere, so there's not that much above there.
But nonetheless, is the composition the same going through the...
So yeah, so I'm going to touch on that next. You're right. So concentrations of nitrogen and oxygen are relatively constant with height, but you can get very drastic variations. So the top one here shows water vapor concentrations, which are also called mixing ratios, and it's a log scale down here, and it has temperature, which is the solid black curve, and then water vapor is the dotted curve. And you can see water vapor, because this is a log scale, it drops the concentration of water vapor drops exponentially with height. And this has to do with temperatures cooling, so the amount of water vapor you can hold in the air depends on the temperature. So the colder it is, so as it gets colder, water vapor precipitates out of the atmosphere, and so that's why these concentrations drop. And another one that changes with height is ozone. And so like I was referring to before, we have the low ozone layer here, and it peaks in the stratosphere, and this helps. This is what's called good ozone because it protects us. You also shouldn't confuse it with the ozone from pollution or in the troposphere, which is bad for health effects. But yeah, so the ozone layer, so that's just another example of that. While nitrogen and oxygen are relatively constant with height, their concentration, some of these gases vary in the vertical. And it also varies temporally as well, so not just in height, but over time. So this is showing from CO2 from the Mauna Loa Observatory in Hawaii, concentrations of carbon dioxide. It's also measured in parts per million, or mixing ratio, so it's how much you get in a given volume. And you can see this is going back from late 1950s when it started up to present day, and you can see the increase in CO2 over time. But what you also notice, so the black curve is the average, so it's like a low pass filter, or just averaging over years moving through it. But you can also see there's these variations that are occurring every year, and this has to do with in the northern hemisphere. So I was pointing out before, there's more land in the northern hemisphere. So in winter time there, CO2 levels peak because you have less photosynthesis. So that's why you can see it's also going changing seasonally, as well as the overall increasing trend, and it's getting up over 400 parts per million. Right. So the next thing we're going to talk about is Earth's energy balance. So we have the sun, and it emits a luminosity, or power, like in the power or energy it emits is 3.9 times 10 to the power of 26 watts. To put that into perspective, your household light bulb puts out around 100 watts. So just showing the order of magnitude of what's coming out of the sun. You can also think of this in terms of irradiance, which is the flux of energy per area. So if you just looked at a certain area right on the outside of the sun, which is the photosphere, you'll measure 6.4 times 10 to the 7 watts per meter squared. So that's how much energy is passing through the surface, a certain surface area.
That's based on the surface of the sun or the
Surface of the sun. So this is the radiance at just the outside edge of the sun, which is called the photosphere. And then because of the inverse square law, which says that intensity drops as a factor of 1 over the radius squared. So as you get further away, the intensity or irradiance diminishes as you get further away. So the separation between the Earth and the sun is around 1.5 times 10 to the power of 11 meters. And you can see once it gets to the top of the atmosphere, the radiance or intensity reaching the Earth is 1370 watts per meter squared. And this value is referred to as the solar constant. And this, as we'll see later, the output from the sun also has a cycle, has an 11-year cycle with it. But
And
yes,
is that what actually reaches the surface of the Earth?
no, sorry. This is what's at the top of the atmosphere. I'm going to touch on that next. So yes, so the total absorbed radiation. So if you take that solar constant and if you think about it, the surface that the sun sees is just a circle at any given time. It just sees a circle, and the area of a circle is pi r squared. And you can use the radius of the Earth, and you can multiply the radius of the Earth by the solar constant, and that will give you the total absorbed solar radiation. But you also have to take into account this the albedo. So the albedo is how much is a fraction of incident or incoming solar radiation that is reflected back to space. And this can be from clouds, can be from ice. It's just, so the average value is around 0.3, so 0.3 of the incoming solar radiation is reflected, so it never touches the Earth's surface. So you have to take this into account, so you do 1 minus AP, so it gives you 0.7. So this gives you the total absorbed solar radiation. And then you have to think about that total absorbed solar radiation as distributed all over the Earth. And then, so if you think about Earth and model it as a sphere, which is pretty good, the area of a sphere is 4 pi r squared. So if you take this value and divide it by 4 pi r squared, this gives you the absorption per unit area. So the energy per unit area that's averaged over the whole planet. And that value, yes. And so we can think about what temperature the Earth would be if we didn't have an atmosphere. So if we didn't have an atmosphere, we can estimate Earth's surface temperature by using Stefan Boltzmann's law, which has to do with the black body. So black body is a theoretical body that it's a perfect emitter and a perfect absorber. So all incident radiation upon it, it absorbs it and then it re-emits it. And so that's why it's called a black body, because it has no color. And so if you think about it, so that what Stefan Boltzmann's law tells you for a black body is that the F is the radiation it's emitting is proportional to this constant times the temperature of the body to the power of 4. So if you take, let's go back. If you take this, so this is the total absorption per unit area, and then so Earth has to be in balance so that what's absorbed is emitted. If you take that and you plug in sigma T to the power of 4, and you solve for the surface temperature, which is the effective temperature of the Earth, this value comes out to around 255 Kelvin, or minus 18 degrees Celsius. So if we didn't have an atmosphere, this would be the temperature, and as we all know, that's way too cold, and the actual observed surface temperature is 15 degrees Celsius. So this tells you the atmosphere has to be important, because else it would be much colder than it is now. So what can be contributing to this? So coming back to John Tyndall, he first measured the infrared absorption of atmospheric gases. So I keep talking about infrared or IR. So why do we keep focusing on this spectrum of radiation? And this has to do with, again, coming back to the black bodies. So you know that depending on the temperature of the black body, so if you model, so this is showing the sun at around 6,000 Kelvin, and so Earth, which is around 303 Kelvin. So the peak wavelength of emission on the black body is inversely proportional to its temperature. So the sun, which is very hot, emits at a very small peak wavelength. So this is showing you the visible spectrum of light, and it emits right at its peak is right in the middle of this, right at the edge of the spectrum of visible light. Well, Earth, since we just saw, Earth is more around 300, and if you take the Earth is 303 Kelvin, around 15 degrees Celsius. Its peak is around in this region here, which is the infrared, so just under 10 microns. It peaks at. So that's why we're interested in infrared absorption, or absorption of atmospheric gases.
No, why, wait, is that peak at 303 degrees Kelvin, is that based
So,
is
sorry,
that
so
means
this
low?
is showing the black body spectrums from, for two different objects. One that's at 6,000 Kelvin, which is this, it's hard to tell here, that's the red one.
Oh.
And then this black one or blue one.
Oh,
is
it's two
at-
different curves.
Yeah, it's
I'm
two
sorry,
different
yeah.
curves, sorry, yeah. So this one, which is black or blue, is at 303 and then this one, the red one, is at 6,000 Kelvin. Right. So what his main conclusions were that nitrogen and oxygen are transparent to both infrared and solar radiation. So these spectrums we see here, both nitrogen and oxygen are, they don't absorb at all from any of the solar radiation, and they don't absorb any of the outgoing infrared radiation from the planet. However, there are certain molecules, like the trace gases I was telling you before, that only make up a fraction or a small fraction of Earth's composition, that are incredibly important, and because they absorb in the infrared. So this is water vapor, carbon dioxide, ozone, and some other gases. And he speculated how fluctuations in water vapor and CO2 could affect Earth's climate. So this is a complicated figure, but I'll walk you through it. So at the top again, so this is similar to what I just showed. The solid red line is showing the black body spectrum of the sun that you would see at the top of the atmosphere. So this is if you're right at the edge of the atmosphere and you're looking at the sun, what spectrum you would see. So don't focus on this part yet. So this is just, the red curve is what you would see at the top of the atmosphere from the sun. And again, you can see it peaks in the visible, and there's a little part, and it goes from the UV and goes down. And then these three curves here are the black body spectrum that you would expect if you were standing at Earth's surface and looking down. So if you're just looking down at Earth's surface, what would you see coming up? And these are the blue curve, which is around 303 Kelvin, and then the other one's just showing at 210 versus the black one, which is at 310 Kelvin. And then we come back to these solid filled parts. So for the one on the left-hand side, this is showing what you would see at the surface of the Earth if you're looking up. So this is telling you how much of the black body spectrum is absorbed by atmospheres in the gas as the solar radiation comes down to the surface. And you can see here, and this is showing the total percent that's absorbed and scattered, and then it shows it for each gas or scattering process. So a large portion is, as you can see, is absorbed by oxygen and ozone. So this is in the UV, so the very small wavelengths. So that's what's absorbed, so it doesn't get down to the surface. And then there's also what's called Rayleigh scattering. So this is scattering because these wavelengths are very similar to the size of molecules in the air, so nitrogen and oxygen. So they scatter it, so they scatter the incoming radiation, so it doesn't even get to the surface and scatters it back outwards. And so you can see, if you look at the sun, you can think of it as these gases taking chunks out of the black body. So they're taking these chunks out of it. So what we see at the surface ends up being this. And
That Rayleigh scattering,
yes, it scatters at the very small wavelengths.
But that's the same, now you have that chart listing oxygen and ozone and
Yes,
methane.
sorry. So so oxygen. First, I'm just trying to point out what absorbs the solar radiation. So you can see some of these molecules. Water vapor absorbs some of the incoming solar radiation, as well as carbon dioxide has like a little band here, and then but a large portion is absorbed from oxygen and ozone and scattered back out from the.
Well, I'm trying to understand the difference though between Rayleigh scattering, because you mentioned that's from.
Sorry, yeah. So
thousands of
Rayleigh
molecules.
scattering is just
How is that different
it's
from
not
that?
absorption. So
Oh,
so here, yeah, I'm showing total. So it's taking the total absorption and scattering. So absorption would be oxygen and ozone absorbing the incoming solar radiation, but scattering is just when you can think of it as bouncing off and just reflecting back
so it's
off.
sent away from the Earth.
Yeah, so it's sent away, so it never reaches the surface. And this is because it's preferential at smaller wavelengths. And coming back on the right-hand side, you can see, so this blue solid curve is what's seen at the top. So say if you're at the top of the atmosphere and you're looking downwards, what spectrum would you see? And you can see it's very different from what you'd see at the surface. And this has to do with water vapor. You can see water vapor absorbs very strongly. It's actually the strongest greenhouse gas in the infrared, so it absorbs a lot. But you also have carbon dioxide, and then other constituents like methane and nitrous oxide, which absorb in the IR. And yes, so overall, and you can also see, so this part here is what's called the atmospheric window. So it's some of the infrared radiation is allowed to escape, but that's only 15 to 30% of it, while almost all of it is being absorbed by the atmosphere. And like I said, water vapor is the strongest absorber, and this is the same that John Tyndall concluded. And another important feature is that the carbon dioxide and the water vapor bands don't completely overlap. So any increase in here in carbon dioxide will absorb much more of this incoming or outgoing infrared radiation. Right. So now with this information on greenhouse gases, we can go back to that model, or that simple model we had with no atmosphere, and then add in an atmosphere and see what happens to Earth's surface temperature. So we have to make some assumptions to do this. The first one is that the atmosphere is completely transparent to solar radiation. So that's all incoming solar radiation gets down to the surface. And then the atmosphere is also opaque to infrared radiation, so that all outgoing infrared radiation is absorbed by the atmosphere. And then so the infrared emission is from the surface and from the atmospheric layer, and we're here in this model, the simple model, we're only considering one layer, so a single slab of the atmosphere. So you can think about it like this. So coming back, this is the same value we had as the radiation that gets down to the surface of the Earth, and then Earth absorbs that, and then it radiates at some temperature outwards. Then you have the atmosphere here, which absorbs all the outgoing infrared radiation and radiates it back both downward and upward. And then, so that you have to take that into account when we're going to calculate the surface temperature of the Earth. But just to figure out what temperature the atmosphere should be at, we know that, so this value, as we found out before, was 255 Kelvin. And so in balance, the radiation entering must be equal to the outgoing radiation. So this means, just by that, that the temperature of the atmosphere is now the effective or emission temperature of the planet. So we know the temperature of the atmosphere, and then at the surface we have this balance, so that the radiation the surface is emitting is equal to both that of the downward from the atmosphere and also the incoming solar radiation. And if we rearrange this equation, we can solve for the surface temperature, and we get a value of around 30 degrees Celsius. And this is better than before, but it's a bit too hot. And this is because of the assumptions we made. So the assumptions again, like I said, there's a window where where some of the IR radiation is allowed to escape, and not all the solar radiation that comes down to the surface. It's absorbed by the atmosphere, and you also have other processes that can transport heat from the surface that I'll touch on later, that are convection and conduction.
Wait, you mentioned there.
Yes.
You mentioned there the temperature of the atmosphere, and then you talked about the temperature of the Earth.
Yes.
But which is controlling that? Is it the temperature of the Earth or the atmosphere? Or is it a combination of both?
So you can think of it as so like these all have to be in equilibrium. So the incoming radiation has to equal to the outgoing radiation, and by just through this simple this assumption, this means that the temperature of the atmosphere now has to be equal to the same value we had before in the case with no atmosphere. And then because the atmosphere radiates both upward and downward in the long wave or infrared radiation, the surface now has in addition to the solar radiation coming in, it has the atmosphere radiating infrared radiation back downwards as well. So you have to take this into account, and that's what causes the temperature at the surface to go up to what we had before. Alright. So we can think about this in terms of energy budget of the atmosphere. So this is more complicated than that simple one we had before, but I'll walk you through it. So this value at the top is the incoming solar radiation. So this is that 370 watts per meter squared divided by 4. So 340 watts per meter squared is coming in. 79 of the watts per meter squared is absorbed by the atmosphere from oxygen, ozone, and some of the other some of the other gases. And then, I was talking about the albedo before. So this is what's represented here. So around 100 watts total is reflected back out to space. So this has to do from both clouds. So there's a contribution coming from both clouds. Then there's a contribution from the surface, from ice, snow, and other areas that reflect the incoming radiation back out to space. So out of the 340 total, 100 is lost or reflected back out to space, which means that in the end, only 161 is absorbed by the surface. And then you can see, so it's coming down, it's absorbed, and then you can also see that this, at the surface it's radiating 398 watts per meter squared back up into the atmosphere. And then what's happening is that it's absorbed by the atmosphere, it radiates it back downwards, and in balance, these are the values of these, of both of them. And then you have this portion here, which is the atmospheric window, where some of the IR radiation is allowed to escape back up. And then the total outgoing thermal radiation is around 240. And if you add the 240 up with the 100, you get back up so that they're roughly equal. So the incoming is equal to the outgoing. And then you also have these processes that also can, radiation isn't the only way you can have energy coming out from the surface. You can also have evaporation and also sensible heat, which is conduction from just having these layers in close contact with each other. Energy is transferred. So this is just an overview of the Earth's energy budget, and these are all measurements that were made. So either from satellites or ground-based instruments that can measure the fluxes of total radiation. And so we can see here that if we add greenhouse gases to the atmosphere, what happens is that it's going to be radiating more energy back down to the surface, and then in turn the surface has to adjust by warming up to emit it back out. All right. With that, we'll move on to the next section, which has to do with climate variability. So there are there's two types of natural climate variability. The first one is external forcing of the climate system. So this has to do with changes in the orbit of the Earth, which affects the amount of solar radiation impinging on the hemispheres during the summer. And like I said before, these can be changed. The Milankovitch cycles can range from 10,000 to 100,000 years. And what's also considered external, even though it's actually in the climate system, it's in Earth, but it's also these large volcanic eruptions. So eruptions from volcanoes will send sulfur dioxide up into the atmosphere that will condense onto particles, and you can think of these as little mirrors in the atmosphere that will reflect radiation back. And I'll touch on these two in a little bit. Another one is the solar variability, so the output from the sun, that 1370 value that I was talking about before isn't constant. It has approximately 11-year cycle. And then the second source of climate variability is internal. So all of these are, you can think of these as external, as like, so these weren't, if these didn't happen, the climate system would be, it wouldn't change, but because of internal climate variability, even without these, you get these nonlinear interactions in a complex system, and I'll talk more about the ENSO, or El Nino, Southern Oscillation. Oh, yes, that's wrong, it's Southern Oscillation. Sorry, no, this is El Nino, then there's also another mode called the NAO, which is the North Atlantic Oscillation. So these are just intrinsic internal variability in the climate system. So, yes, I was talking about before how volcanic eruptions can affect the climate. This is a photo taken from Mount Pinatubo in 1991. You can just see all of the emissions out, and what happens is that when you have these large volcanic events, it inputs sulfur dioxide up into the, right at the top of the troposphere and into the lower stratosphere, and then these condense onto particles and form sulfuric acid, and then these sulfuric acid particles are like I said before, tiny mirrors, and then they reflect the incoming solar radiation back out to space. And this is showing an example of how much, how far you can see into the atmosphere. So it's called optical depth from a satellite. Before and after the eruption of Pinatubo, so you can see just a month after, you have those sulfuric acid particles like just all over focused on the tropics, but then as you get later and further out, it covers the entire globe, and this causes cooling at Earth's surface. So what this is showing is the solid black line is the observed Earth's temperatures, and then also with it are this red line, which is a model, and then lots of simulations from this model, and I'll be talking more about global climate models in tomorrow's lecture, but what you can see here is these lines are volcanic eruptions. So Mount Agung from Indonesia in the 1960s, you had El Chichon, and then you also had Pinatubo. If you look here, you can see a drop in global surface temperatures following these eruptions, because these affect the Earth's radiation budget, where less radiation is coming down to the surface because of these eruptions. And then the other climate force mode of external variability is from the sun. So it was discovered that you have these, you have the sunspots on Earth, you can see on the sun, and that the number of sunspots you see are related to, so this is showing the sunspot number from 1600 out to present day, and you can see the sunspots there's like some sort of cycle on it, and if you, like these like ups and downs going up, and these are 11-year cycles, so this is showing the sunspot numbers along with the solar incident solar radiation, and you can see it varies because it's going up and down, and this is from the 1970s to the present day. So you can see that the incoming solar radiation is related to the sunspot number. So this is also another mode of external variability where you are changing the energy budget by how much radiation is coming into the planet. And although it's hard to see, but you can, so this is again showing what I had before, but then this is the global surface temperature, and if you take an 11-year moving average, you can see that you have these ups and downs in Earth's temperature that are related to incoming solar radiation. And then lastly, on intrinsic climate variability or internal climate variability, you have these what's called the El Nino or La Nina oscillations, and this has to do with, so this is showing sea surface the average sea surface temperature anomalies from December 1982 to February 1983, and you have a large warming of the equatorial eastern Pacific, and then if you compare that to this down here where you have a large cooling of the equatorial Pacific, and these warming and cooling phases are related to, can affect the weather and also in North America, but also all around the world. And because you have easterly from the east winds blowing from east to west, and then during the El Nino phase, you weaken these winds, and this is related with enhanced precipitation across the equatorial Pacific, and in the U.S., because that's where we are, you have more rain in the south and cooler winter temperatures in the southeast. And then in the La Nina phase, which is the cool phase, you have stronger winds along the equator, and that's related to a reduced precipitation across this region. But in the U.S., you have less rain in the south, and winter temperatures are warmer in the southeast. And this is because the atmosphere is, you can think of it like if you hit a bell. So like if you ring a bell in one part of the atmosphere very strongly, you're going to hear it elsewhere in the atmosphere. So that's basically what this is, because these are such large changes in ocean temperatures that it affects the atmosphere and circulation in the northern in North America, and also all the way as far as Europe.
Wait, are those the same thing? Is it like the high end of the cycle is one of those, the low end of the cycle is the other?
Yeah, so this is the El Nino phase where you have warm temperatures over the sea surface, and this is the La Nina phase where you have cooler temperatures over the surface. And then here is showing the related all over the world the changes. So you have with the El Nino phase, which we just had in 2016, you have much warmer. It shows you where it's warm in the world, and in the La Nina phase, it shows you where it's cool, and also precipitation where it's more wet and more dry. And this is just to show you that you can have these fluctuations in temperatures, precipitation, and other conditions that are intrinsic to Earth and not related to the external changes in external forcing. So these would happen without any changes in external radiation coming into Earth.
And what's the primary driver? What causes those?
Right. So that's a very good question, and it has to do with just these modes. Like, so you have these changes in upwelling and downwelling in the ocean, and so if you get if you get enough stress on the ocean surface over time, it's going to accumulate and cause changes in circulation, which will cause both of these events. So it's very, oh yes, up there.
Yeah, also it looks like when the middle part is cooling or heating,
Yes.
the rest of the ocean is doing
That's
the
true.
opposite.
Yes, yeah, that's true. So
Doesn't that balance it out somehow?
well, you have to think in terms of what's causing, there's these where they're called teleconnections or teleconnection patterns in circulation. So you have to think about how it changes the mean state of the climate. And then here, the mean state of the climate are easterly winds. And so if you change the winds, that will change precipitation. And then so these guys are also changing with it, but it's predominantly what's going on in the tropics that's affecting it. Because even though this looks kind of large, it's right in here where you get the most warming and cooling of the sea surface temperatures.
How often does it flip?
Sorry? Oh, so it's not, unlike the sun that I was showing you before where it's relatively 11 years, this changes from 2 to 4 years. So you can have like a year or two where it's in the El Nino phase, then you can have another year or two where it's in the neutral, so it's like normal, but then you can have a year where it's La Nina, and then the next year can be El Nino. So it's not like predictable like this, like the sun where you have the 11-year cycle. It still has a 2 to 4 year cycle in it. Yeah. So that's why in 2016, where we had the record-breaking temperatures all over the world, that was the El Nino phase, where it's predominantly associated with warmer temperatures. So that was helping push it way up above the records. And so, well, the last part I'll quickly go through is changes in greenhouse gas concentrations over time. So what this is showing, the green is carbon dioxide, the orange is methane, and then the red is showing nitrous oxide. And it's showing changes in these three gases concentrations. And you can see some lines here. These lines are when we had direct measurements, so we could directly measure these species. But these circles are what we have to rely on beforehand from ice core data. So so these gases were present in the 1850s, and then you have these bubbles in ice core data. And if you drill further down into the ice, you can go further back in history, and you can get observations from back here that are estimated from the ice core data. So you can see with all three of these greenhouse gases, they've been increasing with time. With CO2 from fossil fuels, methane, you also get it from combustion, but also from land, or sorry, from not agriculture, but yeah, so from agriculture you can get methane, and then N2O is also from agriculture, from the fertilizer, where it's increased as well. So this is just showing that all three of these gases have increased with time, and if we look at the CO2, focus on CO2, so this is showing gigatons of CO2 per year, so the emissions of CO2 using the same thing that I had over the same time period I had before. And you can see it's showing the changes due to forestry, so that's deforestation. And if you burn trees or cut down trees, you'll increase the amount of CO2 in the atmosphere. But since the 1900s, a large fraction of this is from fossil fuel combustion, cement use, which also releases CO2, and flaring or fracking from natural gas. And so you can see this is showing the global anthropogenic CO2 emissions, and compared to 1750, and just showing you the cumulative CO2 emissions. So if you integrate these values over all time up to 1970 and to 2011, you can see how much of it is from fossil fuel emissions and from changes in land use changes. And one question you might ask is, how do we know that the increase in CO2 in the atmosphere is related to fossil fuel emissions? So you can use this method of isotopes. So if you look at the atom of carbon, there's different isotopes of it where you have different neutrons. So you can have different neutrons in the atom. And so you have C12, which has 12 neutrons, C13, which has 13 neutrons, and C14, which has 14 neutrons. And carbon is present in all living things, and life has a preference for lighter C12 carbon, and this is because when plants breathe CO2 and photosynthesis, they prefer C12. So plants absorb C12, and then when they die, they sediment, and then eventually, and same with all other living organisms, this is what eventually goes to fossil fuel. Like the fossil fuels that we're pumping out of the ground are these past living things, and so that if you look at the C13 to C12 ratio, what we'd expect is that it should be decreasing as we're pumping more C12 into the atmosphere if we're burning fossil fuels. And if we look at observations of this, so if we look at observations, so this is again showing global emissions of carbon, and then right here it's flipped so that going up is decreasing. So if you look at the C13 to C12 ratio, it's decreasing with time. So it shows that we're changing the ratio in the atmosphere, and this is from the emissions of fossil fuels, or the combustion of fossil fuels. Right, and so this is again showing the carbon cycle and how much perturbation or changes in the global carbon cycle are caused by human activities. And you can see we're putting out 34.1 petagrams, which is 1 times 10 to the power of 12 kilograms of carbon into the atmosphere. But the atmosphere is only taking 16.4 of this number, and this is because the ocean takes up the carbon dioxide from forming bicarbonate and becoming more, the ocean's becoming more acidic by taking up the CO2, but there's a level of how much it can take up, but it's continuing to take it up. And you can also see that the land is taking, the plants are respiring more of respiring some of this extra CO2 we're putting up into the atmosphere, but that around 16.4 of it is left in the atmosphere. And this is showing that figure, but over time. So if you focus on the top first, this is what I had before with the gigatons of carbon or CO2 going up into the where we're emitting. And then if you look at how much of it is going where. So the dark blue is ocean, so it's showing how much the oceans are taking up. And then the light blue is the atmosphere, so you can look at the atmosphere burden of CO2. And then also the land sink, so how much CO2 is the land is taking up. And you can just see over time a larger portion of it is going into the atmosphere. And the ocean is taking up some of it as well. And the importance of this is because, the importance of this, so this is showing for CO2, if we keep ramping up CO2, so from 1800s to, so this is done with model simulations where CO2 was increased up to, so right now we're just at this 400 parts per million level, and then if you keep increasing it to 550, 650, 750, 850, and then once you reach this peak, you cut off all CO2 emissions, so you're not emitting any more into the atmosphere. What happens? Like, how long does it take for the CO2 to go back down? And you can see, like, even here, if you cut it off at this level, it decreases, but then it stays very high. It still stays high and much higher than it was in the pre-industrial time. And you can see that the more CO2 we keep putting into the atmosphere, the longer it's going to take to get rid of all of this. And this is because there are different processes that can take up the carbon from the atmosphere. Like I was saying, you can have the photosynthesis, and this is a short time scale from 1 to around just 1 to 100 years, but it's the oceans can take it up, but the sedimentation of the carbon that first first created the fossil fuels takes thousands and thousands of years. So this is calcium carbonate sedimentation, also silicate weathering. But this is just to show that all the CO2 we're putting into the atmosphere is going to take a very long time before it can even get back down to this level we had before. Yes?
If you go to the previous slide,
Yep.
why is there the big variability between the three land
Oh, right. So
over time?
what I didn't mention in this is that the ocean part in here is the ocean part. We measure the ocean. We measure the land and the atmosphere, and the ocean is inferred from the rest of it, from the variability. But the variability has to do with, like I was talking about before, but this has to do with the land use changes where you have these large deforestation events coupled with the atmosphere where you can have, like I was saying, the El Nino and other variations that affect plant growth. But yeah, so that's what the interannual variation is due to. And Yes, so this is just to show that it'll take a very long time to remove all this carbon dioxide, which is the important greenhouse gas from the atmosphere, and that every gigaton more of carbon we're putting up, it's going to take a long time to remove it. So, in summary, these trace gases of water vapor, carbon dioxide, methane, and nitrous oxide, even though they're trace and make up a very small portion of the atmosphere, they're opaque to outgoing infrared radiation, and they're responsible for the greenhouse effect. And because of the greenhouse effect, the surface must warm to be in balance. So if we put up more of these concentrations are changing, are increasing, decreasing, the surface of the Earth has to respond by cooling or warming. And that the variability of the climate system can span anywhere from 1 to 100,000 years. And the increase in CO2 since the pre-industrial levels is from fossil fuel emissions, and the removal of CO2 from the atmosphere is a very slow process. And that's it for today, and I'm leaving up here some resources and good books if you want to look into this more, because I don't have time to touch on everything in detail today, but here are a few books you can look at. And you can also check out the Global Change, our website, and look at our educational resources we have online if you want to learn more. And tomorrow I'm going to be talking about how both human and natural caused forcings and how the climate system responds to it, and how we can identify that the temperature changes that we're seeing are related to human activity. So, and I'll take any questions for a short amount of time because I kind of went over, but I'll take a few questions.
Getting back to that El Nino and it's reversed.
Yes.
So what is the fundamental cause of that?
Oh, so it has to do with changes in ocean circulation, where you have because it was first measured because you had stations in one station here and another station here, and they measured changes in temperature, and there was like a connection between both of them, and that has to do with the upwelling and downwelling of changes in ocean circulation. And this is because the changes in the ocean circulation are from accumulated stresses of wind. So you can think of, like I was talking about, the easterly winds. If you keep stressing the ocean over time, it will accumulate until it will just flip, and it reaches these different equilibria, or these where it's stable, but to get from one stable equilibria to another, it's like a sudden shift. So you just get a shift into that, and just like these perturbations. If you look at some of the resources I put up, it'll give a more in-depth view of some climate variability in here as well. Or you can see me after, and I can point you towards some links on it as well for more reading. It's not an easy process. You can do a whole course on just on trying to understand that and modeling it. Yes?
You had mentioned that you can trace the increase in CO2 in the atmosphere to anthropogenic sources because the C13 to C12 ratio is going down.
Mm-hmm.
What is it going down in? Just in the atmosphere itself, like probes in the atmosphere?
Right. So I'll get back to that slide. So if you can take a sample of air. So this is only since the 1980s when you had technology to look at the isotope ratios. So if you take a sample of air and you can measure how many have C12, how many are C13, how many are C14, you can see how this ratio of C13 to C12 is changing over time. And because, like I said, life has a preference for lighter carbon because of photosynthesis, and the plants preferentially absorb C12, and that's what all the carbon in the fossil fuels is. So if we're burning fossil fuels, we're emitting more C12 into the atmosphere, and so if we keep increasing the amount of fossil fuel combustion, we're going to get a higher ratio of C13 to C12.
What you're not saying is fossil fuels have lower C13 ratio. Is that right? You don't actually say what the ratio is for the fossil fuels.
Yeah, so if you look at the C13 to C12 ratio, well, no, it has, it has higher C12. So this ratio, if you're measuring C13 to C12 in the atmosphere, it should be falling as we're increasing fossil fuel combustion because we're putting in more C12 into the atmosphere, because that's more in fossil fuels, the C12. Because like I said, the fossil fuels got there from existing life beforehand.
And what is that, you say there's a preference for C12?
Yeah.
I mean, is
So,
that like
I don't-
mostly C12, or is it like?
I'm not
2%
an
more?
expert in plant biology or this area, but there are people who are experts in this area, and photosynthesis preferentially takes up CO2 that is lighter in the lighter isotope of CO2.
Yeah.
I don't.
But just in a gross way, I mean, is this talking about like a 50% increase in that, or is it just like a few percent? Or?
I
You
do
don't
not
know?
know this.
Okay.
I'm not going to say that, but I can look it up. If you want to talk to me later, you can look it up.
Does the Earth magnetic force have any?
Oh, so changes in the magnetic field? So that happens, I want to go back. So like that slide I had way before of the atmosphere. So the I didn't point it out, but there's something called the magnetosphere, which is above the thermosphere, so it's like the magnetosphere. And that's where, I guess magnetic, like where the flips, like magnetic dipoles or magneticism is. And yeah, so that's taking a lot of these ions that are coming from the sun, and I'm not sure how much changes in the like the magnetic dipole of the Earth affects climate, but I'm not sure how much it is, but I don't think it's negligible compared to what we're talking about here within the troposphere and stratosphere. Yes, come tomorrow and we'll talk about greenhouse gas, or how we can, about forcing mechanisms and feedbacks in the climate system.